Hi everyone, I'm Jay from UIUC, and today I'll be describing a novel approach that gets data down to Earth from satellites in space. This is a joint work with my advisor Deepak and our colleague from Microsoft Frontier. Today's satellites are at the center of spaceflight, with companies like Planet and Capella investing tons of money into building and launching satellites. In fact, in the last decade alone, the number of satellite launches into space has increased tenfold, and this number is expected to increase by another tenfold by 2030. The majority of these satellites are LEO, or low Earth orbit satellites, and they typically orbit only about 600 kilometers off the ground, and it takes them about 90 minutes to orbit around the Earth once. Today, 45% of LEO satellites are Earth observation satellites. They basically take pictures of the Earth from space and send the images down to the ground. And on the Earth, we have these structures called ground stations, which wirelessly receive these images. These pictures can be used for a variety of different applications, like ocean monitoring, agriculture, and disaster monitoring. For example, this image of a wildfire can help with early detection and tracking the propagation of the fire. And given climate change, we can be expecting these natural disasters to be occurring more and more frequently. So satellites become more important as time goes on. However, given that these events are very time critical, it's important that we get these images down from the satellite in as real time and as frequently as possible. To get a better sense of how these satellites image the Earth, we need to understand how they orbit. And looking at this animation, you may intuitively think that these satellites orbit the Earth in a perfect circle. However, if we take a closer look, the Earth is also rotating on its axis. And because of this, the satellite actually moves about offset from its position in its previous orbit. And because of this, it takes the satellite about 5 to 6 days to actually revisit the same point on Earth. And to deal with this, people typically launch hundreds of LEO satellites in these large constellations, where having multiple satellites enables frequent revisits on Earth. So there are a couple of characteristics of LEO satellites that make them great for Earth observation. First is their low orbits enable high resolution imagery. 500-kilometer orbits translates to about 1 meter squared per pixel of resolution. Also, having hundreds of satellites in these large LEO constellations can reduce our image and time granularity down from days to minutes because of more frequent revisits on the same spots on Earth. Also, the hardware on these LEO satellites is constantly improving, enabling new multispectral imaging applications such as UV and infrared. However, as these satellites are orbiting the Earth, they're constantly collecting data, and getting this data down to the ground is a tremendous challenge. A single satellite image is about 500 terapixels, and even if we compress this data, we would still need to send hundreds of gigabytes down to Earth per satellite per day. Also, the problem is that since these LEO satellites are orbiting really fast with respect to the Earth, they only contact with a ground station for about a 10-minute period. For example, as the satellite moves below the horizon and out of view for the ground station, it won't be able to transmit any more data till it comes back around the Earth. So basically, we need to achieve a really high capacity downlink across a long 500-kilometer distance between Earth and space. And the way people do this today is that they build these large, complex ground stations that cost millions of dollars and take a lot of time to set up. And these ground stations have a lot of setup requirements, like buying licensing, buying land, and getting specialized hardware. And because of this, networks typically only set up 4 to 5 of these massive ground stations. And this approach has a lot of shortcomings. For example, we can take a look at the single satellite ground station animation. And as we look, if the satellite moves into this red circle, it can transmit its data down to the ground station. But what we see here is that it's actually taking a while for the satellite to get to the ground station. And because of this, there's sort of this large latency incurred between image capture and image reception at the ground. Also, scaling and trying to build more of these ground stations to compensate for the latency is very capital intensive. Lastly, any sorts of failures, such as bad weather that degrade the satellite ground link, can be very disruptive to the network, given that there's so few ground stations. To address these bottlenecks, we designed a new system, low latency distributed downlink, or L2D2. And at the core of this design is a distributed hybrid ground station approach. What if instead of using the complex capital-heavy ground stations we have today, we instead use these cheap, simple ground stations that can be easily built with off-the-shelf components? And these ground stations can be more easily set up in commonplace spaces like people's backyards or rooftops, and we can scale them out such that they're distributed geographically across the Earth. In the networking community, we've seen a similar sort of evolution as we move from these highly centralized, expensive compute structures like supercomputers to these more distributed architectures like cloud data centers that are based on cheap commodity computers. And the important idea here is that although these distributed architectures yield important benefits in terms of reduced hardware complexity, they pose some significant challenges in terms of increased software complexity. L2D2's design yields some major benefits. First is the network becomes more fault tolerant with more ground stations. Any sorts of failures on parts of the network can be more easily made up by scheduling links in ground stations on other parts of the network. Also, with more ground stations, satellites have a lot more opportunities to transmit their data down to Earth quicker, and this lowers our latency between image capture and image reception at the ground. Lastly, L2D2 is a hybrid ground station approach. Not every ground station needs to be able to transmit. In fact, the majority of L2D2 ground stations are receive only and spend most of their time downlinking images. And this is really important benefit because, as we've seen previously, even companies as large as Amazon take about a year to just get the FCC licensing requirements to build transmit-capable ground stations. So this brings us to the main question of our work. Can a network of these tiny, low-complexity ground stations really outperform the capital-heavy solution we have today? And the answer is an astounding yes, but first we need to address some major challenges in implementing this network. Starting top-down, with so many ground stations and satellites, how do we figure out who talks to who? And today, this is not really a huge challenge since there's so few ground stations and satellites only pass over them for about 10 minutes. But in L2D2, we'll have a lot of ground stations and an increasing number of satellites that are competing against one another for a ground station's link. And we found in our experiments that an L2D2 ground station on average sees about 14 satellites at a time, but in practice, it can only talk to one of these 14 satellites at a time. So scheduling these links is important. So we start by assigning weights to each of these satellite ground station pairs in visibility of each other. And these weights can be determined by signal quality or link quality between the satellite ground station pairs. We can also optimize these links for different aspects of the network, like latency, throughput, or geographic restrictions, such as whether a satellite can transmit to ground stations in certain countries. So this becomes a bipartite graph matching problem. To get some intuition for this, we can start by setting one set of satellites as one set of nodes and the ground stations as another set of nodes. And all the weights in between are the links that we can possibly have with satellite ground station pairs and visibility of each other. And this blue set of weights can be one optimal matching, or this could be another optimal matching, but that's the basic idea. But the problem is, there's another aspect here that makes it a lot more challenging, and it's this idea that the ground station takes time to switch between satellite links. As a result, these matchings are no longer time independent, and we need to optimize the links across time. This problem now becomes NP hard. So to deal with this, we build an approximation greedy algorithm with sticky links. We assign the weights that we talked about previously, and then at time t, we pick the optimal blue ones and ignore the orange ones. But then at time t+1, we need to assign a bonus factor to each of the satellite ground pairs that we picked in the previous time step. And this basically accounts for that cost of switching by incentivizing the ground station to stick to the satellite pair it's already on. We implement this greedy algorithm by using the Hungarian algorithm to find the maximal matching. It converges in OK cubed time, with K being the maximum number of satellites or ground stations. The link estimation and schedule are recomputed and updated about once a day and propagated throughout the L2D2 network. So now that we figured out who talks to who, we need to focus on maximizing the throughputs through the link we have. And to do this, we do data rate adaptation. So rate adaptation is traditionally used in wireless communications in order to maximize throughput through a link. And basically, if we predict a data rate that's too low, or we use a data rate that's too low, and our link quality can support a higher data rate, this is essentially a wasted opportunity as we could be transmitting more through the link. However, if we use a data rate that's too high, and our link quality can't support it, we'll be dropping a lot of packets, which is also problematic. And for satellite ground station links, this becomes even more of a challenge as the link quality widely varies, and there's only a 10-minute transmission window to get all our data to the ground. So picking the ideal data rate is very important. In traditional satellite ground systems, feedback is typically used from a transmit-capable ground station to the satellite in order for the satellite to send at an ideal data rate. However, in L2D2, we have a majority of receive-only ground stations. And these ground stations can't send these ACKs to the satellite. So basically, what we need to do is predict this link quality and the ideal data rates to send at before the satellite even passes over the ground station. So we need to understand, to get a better intuition of this problem, why this link quality varies. And we can take a look at the SNR over time for a satellite ground link. Basically, the higher the SNR, or signal to noise ratio, the higher the link quality. So what we see here is that at the beginning, as the satellite moves into view of the ground station, the SNR increases, and towards the end, as the satellite moves below the horizon and out of view of the ground station, the SNR decreases. But towards the middle here, we see this dip in the SNR. And normally we'd expect the SNR to be at its peak here. However, we actually see that this is due to environmental losses, such as multipath reflections on both the satellite and ground station that are causing this link degradation. Lastly, we also want to plot the same satellite ground station link, except on a different day when it's raining. And accordingly, we see the overall SNR decrease. So using the factors we talked about, we can build an ML model for every satellite ground link to predict SNR and data rates over time. We implement this model by generating weather features from weather forecasts and generating satellite position features by using two-line elements for every satellite in our network. Then with these satellite and weather features, we feed them into an ensemble model of tree boosting and neural net architectures, which both output the SNR, and effectively we can leverage machine learning to predict the ideal data rate this way. However, even with the ideal rate adaptation and scheduling algorithms, we still will have packet loss. And the problem is that in L2D2, we have receive-only ground stations that can't send ACKs to the satellite. So the way we handle this is that whenever a satellite transmits data to a receive-only ground station, that station will send a notification via internet to one of the TX-capable ground stations in L2D2. Then when that satellite passes over the ground station, it'll relay the acknowledgement on behalf of the receive-only ground station. And effectively, this way, we're able to implement ACKs in L2D2 with some delay. And this is really helpful because the satellite will know which data it gets to the ground successfully and what data it needs to send again. So now we evaluate L2D2 by starting with the link estimation algorithm. We use real-world measurements from 5 ground stations and 4 satellites in common Earth observation frequency bands. For every satellite ground pair, we have measurements for about 1 month, and we train a subset of these measurements for our model and use the other subset to evaluate our model. And these data sets have been made public, and I encourage you to check them out at the link below. Here's a map where all the ground stations in our data set. And now we look at link prediction accuracy. On the x-axis here, we have the SNR error in dB, and on the y-axis, we have the cumulative distribution function, or CDF. Here's our L2D2 model, and we compare it against the state-of-the-art model from the ITU, which uses weather features and satellite positions to mathematically predict the data rate and the link quality. So basically, what we see here is that L2D2 significantly outperforms the ITU model in terms of SNR error. In fact, at the median, the ITU model has about 2.5 dB worse SNR error. What this translates to in terms of median data rate error is about a 6.25% reduction from the optimal link in L2D2, but a 41% reduction from the optimal data rate in ITU model. And this is a really important finding because L2D2's link estimation algorithm drives other aspects of our work, such as finding the weights for the satellite scheduling algorithm. It also can be used for other applications beyond L2D2, such as ground station planning based on where the optimal satellite predicted links would be. We also set up a large-scale evaluation for L2D2 by first starting to look at the SatNOX open source ground station network. Here we gather positional and ground station information from real-world satellites and ground stations. However, since SatNOx is typically only operated in low frequency bands and is only used for applications like satellite beacon finding, we found it more representative to emulate the high frequency links for our Earth observation application with the measurements we talked about earlier. In our experiments, we have each of the satellites generate about 100 gigabytes of data per day, and as they orbit the Earth, they transmit data down to ground stations they see. We also wanted to compare L2D2 against a state-of-the-art model, so we picked 5 of these ground stations and designed them in such a way that they have at least 10 times higher median throughput than L2D2. So latency is the name of the game here. On the x-axis, we have our latency in minutes, or time between data capture and data reception at the ground. And on the y-axis, we have the CDF. So here's our baseline state-of-the-art model that has about 1.5 hours of latency at the median and 5.5 hours of latency at the 90th percentile. But at L2D2, we only have 20 minutes of latency at the median and about an hour of latency at the 90th percentile. And what we see here is that with more ground stations, satellites have more opportunities to transmit their data to Earth faster. But we also wanted to isolate the benefit of geographic diversity alone. And to do this, we basically took a 25% subset of L2D2's ground stations and ignored the rest. And what we find here is that L2D2 25% still outperforms our state-of-the-art ground station network in terms of latency. And what's interesting is that L2D2 25% has an overall lower aggregate capacity than the state-of-the-art network. And what we see here is that basically our distributed ground station architecture can reduce our latency from hours to minutes. So L2D2 can be compared to some prior related work. Prior architectures in ground stations such as Lockheed Martin's Verge or SatNOx and GENSO also have this same sort of distributed receive-only approach. However, they're typically used in low bandwidth downlink applications and are not really representative for us. And unlike them, L2D2 has a hybrid architecture where some ground stations are transmit capable. Also, there have been many prior satellite ground station scheduling efforts. However, in general, they've been less sophisticated than ours and don't account for link variation over time and are limited to single ground station multi-satellite architectures. Also, there's been some prior work in satellite ground link estimation. However, they've mainly been carried out over simulated data or low frequency links. And like we've shown before, L2D2 outperforms prior statistical models. Ultimately, what L2D2 proposes is a new ground station architecture that's low cost and distributed. And what it can do for us is reduce our latency from these LEO Earth observation satellites. And basically, one last point to mention is that the real world measurements that we use in our experiments have been made public, and I encourage you to check them out below if you're interested. Thank you.